Just not good with the ladies, like you said.
All right. Try this on her. Hi, I'm Paul. You have beautiful eyes.
Hi, I'm Paul. You have beautiful eyes.
I'd love to take you out sometime.
Love to take you out sometime.
So how much?
So how much?
With a great taste that won't fill you up and never let you down. Make it a Bud Light.
Okay, guys, here's a question for you. Boxers. Why do they bother with gloves? Why not have these athletes go at it without gloves? What's the big deal? What's the worst that can happen if they're going at it without gloves? Any ideas?
Serious injuries.
Okay, so what kind of injuries are we looking at?
Like potentially broken bones.
100%. Yeah, I mean, broken bones. The amount of force required to break somebody's cheekbone or face is probably the same amount of the energy required to break somebody's hand, right? All right. I mean, if you hit someone so hard to cause an injury or broken bone in the face, it's probably the amount of force required to break your hand. Okay, so I mean, these are well-trained athletes, and you can just have them go at it. And if you have them go at it, number one, it's probably not going to be as interesting, and also it's not going to last as long. All right. If you're looking at the boxing videos, I'm surprised I don't have any from 60, 70 years ago when they didn't have gloves, or they had something. I don't remember exactly what they had. The style was boxing completely different. Because people didn't want to injure their hands. So they used to hold their hands like this and that because they were not able to go wild gyrating motions and uppercuts and that sort of stuff, because they knew that if you're going to try to break somebody's face, more than likely you're going to end up breaking your hand. So wearing a glove, what's the advantage of that? I mean, does it reduce the impulse, you think?
No, the impulse would still be the same, but it would increase the time, so it would decrease the force.
All right, give yourself 20 points with that one, because this is more of a trick question. Guys, the impulse is going to be the same. I got to tell you, with or without gloves, impulse is going to be the same. Someone hitting you in the face with gloves or without gloves, it's going to be the same. You got news for it. For example, I love Tyson. I'm a big fan. I used to spend a lot of money paid per view back. He was the king in the late 1980s when I was a college student. That was a complete waste. All right, because that guy, literally, you pay $20 just to watch him box, and then you just drink beer, and then now you have to go to the bathroom. By the time you would come back, it would be done with. It would be that fast. I'm gonna say he no longer boxes, obviously, and then it almost. I can create the impression that you can pick a fight with him. That guy can take my face from 0 to 100 miles per hour, with or without a glove, and result is gonna be the same, guys. All right, so velocity on my face is gonna go from 0 to 100 regardless. That's your impulse. That's your impulse. If he's wearing gloves, though, I got a story to tell. If he's not wearing gloves, who knows what's going to happen? All right. Either way, my face is going to be moving at 100 miles per hour. So the question is, what do the gloves do? It's not going to change the impulse. It's the same impulse. The impulse is changing momentum, right? So my face literally is going to go from 0 to 100 miles per hour. Except the only thing it does literally is increase the impact now, reduces the force. In turn, the damage is going to be lessened. Either way, my face is going to go at 100 miles per hour. He's going to knock the shit out of me, basically, regardless of it. But one of them is more than likely survivable, and without the gloves, who knows? All right, so this week's factor is destination of electron acceleration. So the acceleration is how fast the velocity changes in time, how fast you speed up, how fast you slow down, how fast you change direction, right? All right, so acceleration is what kills, what breaks your bones, what maims you. Okay, you're not going to be able to change your initial velocity or your final velocity. All right, I mean, this guy is going to take my face from 0 to 100 miles per hour regardless. That's what's going to happen. This guy is that strong. I can influence the impact time. If I influence the impact time by making it larger, I may be able to survive the incident, which means that I can reduce the acceleration. Because we know what's survivable is not. No, you can survive between 7 to 12 Gs, up to a few minutes. You can survive between 20 to 25, up to a few seconds. You also know that you can survive up 100 to 140 Gs for a fraction of a second under extreme constraints. All right, so those are what's considered survivable. So the question is, how do you go from acceleration to something a little bit more powerful? All right, so impact, collisions, whatever. You end up getting jerking motion, which means that you end up getting a variable acceleration. All right, so if the acceleration is variable, what do we use? We use the average acceleration formula for it. The whole idea of making impact survivable is to increase the impact time. All right, so increasing the impact time, that's going to reduce your acceleration. So acceleration by definition is how fast the velocity changes in time. That's how fast the velocity changes in time. So you go from initial to final velocity within a certain time period. All right, acceleration is a vector, so it's going to have direction. All right, what causes acceleration is a force. So force acting on this mass is going to cause it to accelerate. Acceleration is how fast the velocity changes in time. All right, so get rid of the duration or the time. right? Multiplying both sides by the time or the duration. And you come up with an expression that's going to have a combination on the left-hand side of the force and its duration. And so when there's a force acting on a mass for a certain time period, just like this delta t is, what it does, it causes the motion to change. So which means that the velocity changes. All right. So the velocity of this mass changes. The velocity of this mass, combination of mass and velocity, is known as momentum. All right. So the combination of force and its duration is known as impulse. So what happens during impulse? There's a force acting on this object. It changes the momentum of that object. So that's your impulse. Impulse is a combination of force and its duration. And what happens during impulse is the velocity is going to change, which means that the momentum is going to change. So momentum is the same as motion. Newton used to refer to it as motion, so that's what it is. So that's how it stays. All right, so I think we did the derivation already. So okay, let's go back, highlight it. Okay, a couple of things to highlight. So this is known as the impulse momentum theorem. All right, so impulse is a combination of force and its duration. So I is impulse. Delta t is the time or duration. Force by definition is mass causing acceleration. All right, so impulse momentum theorem comes out of Newton's second law in essence. So this is your second law. All right, do a back substitution. Acceleration, in this case, we're dealing with the average acceleration. Average acceleration is going to give us an average force. All right, t here is the same as delta t here, so delta t is going to cancel. So this is going to give you a change in velocity for this mass. Combination of mass and velocity is going to be momentum. All right, so what happens during impact is the momentum changes in impact. All right, so force is the average force, delta t is your time. All right, so let's come up with a single expression summarizing everything that we discussed. So impulse is a combination of the average force and its duration of that average force. So what happens during impulse? The momentum changes the impulse, which means that the velocity of this mass is going to change in impulse. So this statement is the same as this statement from the formula sheet, except delta t becomes t. Change in momentum is a change in velocity. Obviously, I have to skip that. And momentum is mass moving at a given velocity. All right, so let's do a lecture review. So what's impulse? It's going to be a combination of force and its duration. So what happens in impulse is the momentum changes. So impulse changes momentum. What's momentum? It's the mass moving at a given velocity. All right, so velocity is the speed and its direction, right? All right, so if you're speeding up, that means that your velocity is changing. If you're slowing down, that means that your velocity is changing. If you're changing direction, that changes velocity, also changes momentum. All right, so why to use the average force in impulse calculations? Guys, at the end of impulse means collisions, which means that there's impact, which means that there's variable acceleration, which means that there's jerk in motion. If there's jerk in motion, what do? Use the average acceleration formula. Right, so acceleration is caused by a force. So what gives you a variable acceleration is a variable force. So which means that you have to use the average force. All right, so what happens? The momentum during impulse, what happens? Momentum changes, which means that velocity is changing. Velocity changes during impulse. So what happens to force if the duration of impulse is short? If the duration of impulse is short, the force gets larger. So if you reduce, all right, so impulse is change of momentum, obviously. So for a given impulse, if you reduce the impact time, it's going to increase the impact force. If you increase the impact time, that's going to reduce the impact force. Okay, so boxers wearing gloves, it's not going to change the impulse. In my example, my face is still going to go from 0 to 100 miles per hour, punched by Tyson, obviously. So that's your impulse. It's not going to change. If he's wearing gloves, it's only going to increase the impact time, so that's just going to reduce the acceleration. So it's going to reduce the impact force. It's going to make it more survivable. All right, so what's the unit for momentum? Mass is going to be expressed in terms of kilograms. Speed is going to be expressed in terms of meters per second. So impulse is going to be kilograms to meters per second. Impulse is, you got the force, it's going to be in terms of newtons. Time is going to be in terms of seconds, so it's going to be newton seconds. All right, so impulse and momentum will have the same units because impulse will change momentum. So which means that both of them could be expressed using the same identical units. Doesn't matter which one you use. We'll have the same units. That's weird. I missed something. Okay, forward.
Troy's plan is to enter a grizzly's den and extract a blood sample from a sleeping bear, and the grizzly-proof suit is the only way he can do it.
You can't get close to a grizzly. It'll kill you. If you haven't got protective means like I do, you're dead.
Troy recognized the need to get close to the grizzly early in his research.
My first year of college, I watched the preview of RoboCop. I said I could build one of these, and this is my research vehicle.
Reaching this stage of development was a long, difficult, and painful journey. He named the first suit, created in 1985, the Ursus Mark I, after the grizzly's zoological classification, Ursus arctos horribilis.
The first suit was simple hockey, baseball, lacrosse. I had 12 different sporting equipment because that's the only amount of money I had, and that was the best plastics they had. Well, that was thrown away in an hour. I mean, a simple half swing with a baseball bat break your arm.
3 years and 4 suits later, Troy creates the Ursus Mark V, constructed of more durable equipment like ski boots and motorcycle gear. Troy's tests grow more intense to replicate a grizzly's phenomenal strength. The trials border on the lethal. Troy's research assistants use wooden bats to test the strength of the suit's outer shell. Swings to the face test the durability of the headgear. Troy is shaken, but not injured. He decides to increase the force. Troy still isn't satisfied, so the punishment continues. A 150-pound sandbag, swung from a height of 25 feet, strikes Troy directly in the face. The blow levels him, but does no harm. Troy believes this suit is ready to face a full-grown bear. A 3-ton truck moving at 25 miles per hour.
If you can handle that truck 50 kilometers an hour, I have no problem with anything a grizzly bear can do.
To be sure, Troy increases the speed to 30 miles per hour. After this test, Troy concludes that the suit needs improvements.
I think Troy needs some improvements as well.
Troy
So what's the whole purpose of the suit? Increase the impact time, right? Makes it more survivable.
swings to the face test the durability of the headgear. Troy believes this more intense.
If you can handle it.
Temporary kung fu practitioner.
Guys, let's do a mind twister.
The existence of chi has never been under question. When properly focused, this is the energy that enables them to transcend the physical limitations of flesh and blood and perform feats that appear to
I've seen people break a single brick before.
challenge the
I've never seen what he's about to do before, though.
impossible.
The first one is broken. So is the second one. So is the third one. So is the fourth one. Wow. Impressive. All right. So, of course, they could just set it up in such a way that he breaks one of them and the other 3 are broken, but we didn't notice it before. Let me just set it up for you in the following fashion. All right, let's compare this guy to another guy who's just as strong. And another martial artist who happens to be just as strong, except the other guy is only going to be able to break 1 brick at a time. All right, so this guy clearly ended up breaking 4 bricks with a single strike. And the other guy is going to be just as strong, except he can only break 1 brick at a time. All right. So the fact that this guy is able to break 4 bricks with a single strike, does that make him more powerful? All right, let me ask you, who do you think is more powerful? All right, given the fact that he's able to break 4 bricks with a single strike, does that make him stronger or more powerful than a guy who's able to break only 1 single brick at a time? What do you guys think? All right, this is a bit of a mind twister. Does that make him stronger or does that make him more powerful? All right, guys, what do you have? Okay, hold on. There are comments. I'm not able to see the comments. Okay, so for those of you guys who are saying more powerful, what do you mean? Okay, so those of you guys who said more powerful, okay, so they could be equally strong, right? In terms of, let's assume that we got 2 guys, both of them are martial artists. They're equally strong, which means that they could lift maximally the same amount of weight. So let's just pretend that they're going to be able to lift the same amount of weight. So which means that they're equally strong. All right. So the question is, the guy who's breaking 4 bricks with a single strike, how is it that he's actually more powerful? All right, guys, what do you have on that?
Is it something like they're able to decrease the impact time and thus more force goes through?
Okay, that's not bad. Okay, so let's think of it. If you reduce the impact time, okay, so power is how fast the work is done, right? All right, so how fast the work is done, how fast the energy is transferred, how fast the energy is converted, either way. All right, so the shorter the impact time is, larger the power is going to be, right? All right, so shorter the impact time is, the larger the power is going to be. That's what it means. Okay, let's skip to the same thing. How about the impulse? Do you think in both cases, they deliver the same impulse? The guy who's breaking a single brick versus a guy who's breaking 4 bricks at a time, are they delivering the same impulse? Okay, so they have the same strength. They're not equally powerful. The guy who's breaking 4 bricks is actually more powerful than the other guy, despite the fact that they're equally strong. How about the impulse? All right, do they generate the same amount of impulse? What do you guys think? Okay, these are interesting mind twisters. Hold on, I'm just noticing that I'd be probably slightly better if I had my iPad. All right, so the guy who's breaking 4 bricks at a time is moving his hand much faster than a guy breaking 1 brick at a time. Okay, so what do you suppose the reason for it is? Okay, guys, here's the reason. All right, you guys are next one. First, a novice.
The computer displays the results. First, the novice.
Novice versus expert. What's the difference? Impact time is much shorter in the case of the expert, right? Why? Because his hand is moving much faster. The question is, why is that his hand is moving faster than a novice? Guys, you're a novice. I'm a novice. Most of us are novices. I've never broken a brick before by hitting it. All right. But I can move my hand just as fast as an expert does. There's no question about it. Okay. You can come up with the same technique. You watch the guy a couple of times, couple of tries, you can execute it just as well. Except that guy is going to be able to break the bricks maybe 100% of the time. And if I'm lucky, I'm probably going to break one after I try 20, 30 times. All right, what's the difference? Difference is confidence. Difference is confidence. The expert, this guy had done it 1,000 times. So he's gonna move his hand regardless, and he knows he's not gonna break his hand. All right, he's got that understanding. He had done it 1,000,000 times. If I'm a novice, I'm afraid that I'm gonna hurt myself. So I may make it look like I'm doing a good job, but in the last second, you will just. So it's the difference. All right. The more powerful guy is more powerful in the sense that he was able to transfer the energy faster. Both of them are equally strong. All right, both of them are equally strong. The guy who's more powerful is able to transfer the energy more. Okay, so the next question is, let's do a comparison. Who's going to be able to generate a larger impulse? The guy who's breaking the brick or the guy who's not breaking the brick? What do you guys think?
I think it's going to be the same.
All right, so who's generating a larger impulse? Now, you have to go back and think about the meaning of impulse. So what's impulse in this case? Impulse is change of momentum, right? Change of momentum. So change the momentum of the hand. What happens to change the momentum of the hand? Let's pretend that you're going to hit the brick at 50 miles per hour. So your hand is going to go from 50 miles per hour to 0 if it doesn't break, right? And if it breaks, okay, your hand is going to slow down, but the change of momentum is going to be smaller, right? Okay, in reality, breaking a brick is going to generate a smaller impulse, believe it or not. It's going to generate a smaller impulse. The impulse is going to be smaller if you can break it. Impact time is going to be shorter, which means that the force that you're generating is going to be larger during impulse. Okay, despite the fact that both guys are equally strong, the guy who's actually breaking the brick is generating a larger amount of force, and the other guy who's not breaking it is not hitting it with the maximum amount of force that he could. That's the difference. He's generating a much larger impulse, but his impact time is much larger. As a result, the force is not large enough to break the surface. All right, so in essence, the guy who's breaking the brick, despite the fact they're equally strong, that guy's hitting it with his maximum strength. The other guy's not hitting it, not as fast. That also means that the amount of force that he's generating is not large enough. Okay, that's an interesting way of looking at it. All right, let's try to come up with the best answer. Okay, let's just put your answer in the chat. Put your answer in the chat. All right, we got 6, 7, 8, 9, 10 responses. Okay, so it's the action and reaction force, right? So, which means that the forces will be identical. So you guys got that. Beautiful. All right, you guys didn't get fooled. All right, so that was good. Action and reaction force. Conservation of momentum is the concept that we're focusing on this week. All right, so it's a head-on collision between A and B. It's exactly the same as hitting a brick or a person getting hit by a train. Or head-on collision between a car and an SUV. Action and reaction forces will be the same. So action and reaction force in both cases will be the same. All right, so let's go over the derivation one more time for this one. So head-on collision between two masses, mass 1 and mass 2. Action force is acting on mass 2, and the reaction force is acting on mass number 1. Okay, let's take a look at the impulse. Impulse generated both masses. Impulse generated on the first mass is going to be due to the reaction force. And the reaction force is going to act on this mass for a duration of delta t. So what happens during impulse, the momentum is going to change. Its motion is going to change. Its velocity is going to change. It's going to go from an initial to a final value. Likewise, the action force is going to act on mass number 2 for this duration. And what happens is velocity of the second mass is going to change within that duration. So we're looking at the total impulse of the system. Okay, so the system is known as an isolated system. Whenever we talk about a system, we're dealing with a system of colliding or interacting masses, the objects, the particles, depending upon the situation. So we're dealing with the mass of the interacting masses. We're dealing with the system of interacting masses. And we're looking at the total impulse of the system, not impulse of the individual items. We're looking at the total impulse of the system, a system containing these colliding objects. So you take the impulse of the first one, it's reaction force and its duration on the first mass, action force and its duration on the second mass. Notice that the durations, the impact times are the same. So you factor that out. Then you have the change in velocity of the first mass plus the change in velocity of the second mass on the right-hand side of the equations. Right, so this is the statement of the net force. What does the net force do? Net force usually is what causes acceleration. All right, so the net force, external net force, is what causes acceleration. You got the net force here for acting on a duration on these two masses. What's going to happen is one mass is going to undergo a velocity change, that's acceleration. The second mass is going to undergo a velocity change, so that's also acceleration. Except the net force is going to be generated by the action and reaction forces. And action and reaction forces will have equal magnitude and they will be in opposite directions. So which means that the net force acting on the system is going to be 0. Okay, guys, net force acting on an isolated system is going to be 0 because you're interested in the net force acting on the system. The system is composed of colliding particles. Any force between the colliding particles become internal forces. Internal forces do not cause acceleration. All right, if you wanted to get up from the chair that you're sitting on, you have to apply a force on the ground. The ground is going to apply the same force back on you. As a result, you're able to get up. So the reaction force from the ground becomes the external force acting on your body that allows you to be able to get up. You cannot grab the other arm and then try to pull yourself up. Internal forces would not allow you to accelerate. Okay, so net external force acting on an isolated system becomes 0. All right, so that's what it means. Which means that the impulse is going to be 0, which means that change in momentum is going to be 0. Okay, so change in momentum of an isolated system always going to be 0. All right, so this would be mass into the parentheses. So this is the change in velocity of the first mass. This is the change in velocity of the second mass. And gather the final velocity term from the left-hand side and the initial velocity terms on the right-hand side. Okay, so this represents the total momentum of the system before the impact or collision. This represents the total momentum of the system after the impact of the collision. I want you to realize that the total momentum after is going to equal to the total momentum before. All right, so we're always dealing with the total momentum of systems from now. And this is a really powerful method of solving problems. So the final momentum here is going to be this. Initial momentum is going to be that. So the initial momentum is on the right-hand side. The final momentum is going to be on the left-hand side. So total momentum of a system before and after, they will be the same. So this is known as constancy or the conservation of momentum. All right, so that's a mathematical way of looking at it. That was a derivation, so you could see where the concepts are coming from. What you need is the interpretation of it. All right, so the interpretation of this concept. Okay, so I did the derivation, I think. Okay, yeah, we did the derivation. Okay, that is the derivation. All right, so conservation of momentum from a math perspective. In the absence of an external force acting on an isolated system, only forces are internal forces, or action and reaction forces. Action and reaction forces will become the internal forces of a system. Internal forces will not cause the system to accelerate. That's what it means. So, which means that the total momentum before impact and the total momentum after the impact will be equal to each other. So that's the model that we're pursuing. Okay, so next thing I want to do is just want to make sure that you have a good understanding of what's going on. So let's express things conceptually. So the question is, what happens to the object's momentum if there's a net external force acting on it? Okay, so let me just emphasize the term on the object's momentum. We're not talking about a system, you're talking about a single object. Okay, so what happens to its motion if there's a net external force acting on it? Guys, if there's a net external force acting on the mass, which means that there's going to be impulse, it's going to change the momentum of that object. All right, in fact, if you isolate the force in this equation, you end up getting force causing change in momentum within this duration. Momentum is obviously the mass going at a given velocity. So what's happening because of the force, the velocity is changing. Change in velocity in time is going to be acceleration. So net external force causes the object to accelerate, which means that net external force causes the velocity of the object to change. And what that means is the net external force is going to cause the momentum of that object to change. Okay. So far, we've been expressing the force in terms of acceleration. All right, and from time to time, we're going to start to express it in terms of change in momentum. All right, it's a much more powerful expression than mass accelerating mass. So much more powerful than, in fact, equation E equals mc squared came out of expressing force in terms of change in momentum. So that's just a very powerful mathematical method. All right, so if there's an external force acting on a mass, what's going to happen? It's going to accelerate, which means its velocity is going to change, which means that its momentum is changing. Its velocity is changing, its momentum is changing. The next question is, what happens to the momentum of an object in the absence of a net external force? So what happens to the momentum in the absence of a net external force? Guys, if there's no force acting on it, what happens? There's no change in momentum. All right, there's no acceleration. If something is moving to begin with, it's going to keep on moving in a straight linear constant speed. So velocity is not going to change. If something at rest, it's going to remain at rest. So which means that now you fall back to Newton's first law. So that's known as inertia. So nothing is going to happen. It's just going to remain constant. Isolated system is a system that only concerns itself with colliding objects. Two masses colliding, that's your isolated system. Head-on collision between a car and an SUV, that's your isolated system. Car and an SUV. Person getting hit by a train, that's your isolated system. All right, so isolated system is a system that only concerns itself with the colliding objects or interacting objects. So what's the net external force between two colliding objects in an isolated system? Between two colliding objects in an isolated system, you only have action and reaction forces. Okay, so action force is going to act on a small mass, the reaction force is going to act on a big mass. But notice that action and reaction forces of an isolated system will become internal forces. They're going to be equal to each other in opposite directions. So this force summation is just going to add up to 0. So the net force of an isolated system is going to be 0. Right, so it becomes an internal force. So net force becomes an internal force, and it's 0. So which means that the isolated system itself is not going to accelerate. So the next question is, what happens to the total momentum between two colliding objects in an isolated system? It's not going to be a change. Total momentum is not going to change. Total momentum before and after will be equal to each other. That's what it means. Change in momentum of one object is going to equal to the change in momentum of the other object. That's the meaning of it. All right, so the momentum for each mass is going to change the same amount. So what's the meaning of conservation momentum? Conservation momentum simply means the momentum is going to remain constant. And the final momentum will be the same. So the next question is, what conserves momentum? Absence of an external force on an isolated system. What conserves momentum is an absence of an external force on an isolated system. So the net force acting on an isolated system is going to be 0. All right, so let's go back. What is supposed to be a lecture review? Lastly, what's elastic collision? What's an elastic collision? Elastic collision, every collision is going to conserve momentum. If it's an elastic collision, kinetic energy is also conserved. In elastic collision, the kinetic energy is not conserved. So the elastic collisions will conserve kinetic energy. Inelastic collisions will not conserve kinetic energy. So that's the difference. All right, so every single collision is going to conserve momentum. All right, so you got approach, you got collision, and what happens right after collision, depending upon the type of collision. If it's elastic, kinetic energy is conserved. If it's inelastic, kinetic energy is not conserved. So that's the difference. All right, so speaking of collision,
defensive back, hit the runner with enough force to reach. He's going to keep trying to the contact with the two colliding bodies. When a quarterback is chased by a lineman, he's at a.
all right, those of you guys who don't know, this guy quit playing like 20 years ago. One of the best quarterbacks ever. He's like 5'7", 5'8". It was quick as hell. It's impossible to catch. Now I noticed that he's going to get tackled. Boom. Okay, so what kind of collision is this? Elastic or inelastic? And why? All right, so what's the difference between elastic and inelastic? If it's elastic, kinetic energy is conserved. If it's inelastic, kinetic energy is not conserved. So what do you think? This is elastic or inelastic?
Inelastic.
Okay, give yourself 5 points. Why is it inelastic? Well, kinetic energy is not conserved, which means that the kinetic energy must have been converted to something else, right? So the question is what?
There is always an equal and opposite reaction. Variations in player size, speed, and direction have different effects on the two colliding bodies. When a quarterback is chased by a lineman, he's at a tremendous disadvantage.
You guys hear the sound? Where's the impact? So it gets converted into sound. What else? And it get converted into this, and then there's tons of deformation there.
The lineman.
All real life collisions will be inelastic. Okay, guys, real life, there's no conservation of kinetic energy in real life. There's always, there's sound is going to be generated. If there's impact, there's going to be sound. There's going to heat is going to be generated. There's going to be some sort of deformation. Only in idealized cases, you end up getting elastic collisions in idealized cases. All right, if there's any sort of force transference, for the most part, kinetic energy is not for the most part, nearly 99.999% of the time, you end up getting inelastic collisions. So which means that kinetic energy is going to be lost.
More massive and moving with greater momentum, faster than a quarterback getting ready to.
I'm just trying to think of a case where the kinetic energy is conserved, okay, in particle physics, in small objects or whatever. Obviously that happens. With solid objects, big objects like that, it's just there's always going to be some sort of deformation.
Throw.
The mechanics that we were dealing with, I cannot imagine a case where you end up getting an elastic collision.
As a larger player transfers
When you're dealing with molecules and atoms and whatnot, if they are neutral,
most of his momentum to the quarterback finds himself moving in the direction of the lineman's momentum.
yes, but not in these cases.
So, Professor, where does
That's probably
Well, there is more controversy surrounding the MTV show that is called Jackass. A Kentucky teen recently broke bones.
Potentially avoid being hurt. The boy stood in front of his friend's car. He would have to jump several feet straight up into the air to avoid being hurt. It was impossible.
Okay, guys, if the car is going at 30 miles per hour, the guy's going to be moving at 60. The
He would
car,
have to jump several feet straight up into the air to avoid being hurt. It was
the car is going at 40, that guy's going to move at 80 miles per hour, give and take. The car is moving at 50, the person getting hit is going to move roughly about 100 miles per hour, roughly.
impossible.
So action force acting on him is going to be about 40,000 pounds. Reaction force is going to be acting on the car, so it's going to be about 40,000 pounds. So same force acting on the car, if the car is more massive, acceleration of the car is going to be smaller. The car is going to go from 30 miles per hour to about 29 to 28 miles per hour.
Happened was a car hitting here
Where am I getting those numbers from?
and then
His friend's car. Attempt to stop several feet.
up in the air.
You have to jump several feet
All right, so this is called deja vu, guys. We had this discussion before.
straight up into the
The train is going at 60, the person getting hit is going to end up flying off at 120 miles per hour, almost. Almost double the speed, almost double the speed.
air to avoid being hurt. It was impossible.
Acceleration of the train is not going to change that much. The train is going to have a very small acceleration because it's very massive. The person is going to have a huge acceleration because the person is not as massive. Where am I getting these numbers from? I said, I'm getting those numbers from the conservation of energy and momentum principle. Oh, that's what we will discuss. All right, if you take a look at this, notice that at the moment of impact, if my hand is moving at 5 miles per hour, this thing is going to move at double the speed. In fact, it moves out of the way so fast that I can move my hand right after the impact without touching it again in reality. All right. So why is it? It's not, the question is not why. The question is, where am I getting those numbers from? Okay, so that's what I want to discuss.
The 16.
All right, so this is the problem in this case. So we got a car. It's going to be problem number 8. So the amount of force, action force is acting on the person. The reaction force is going to act on the vehicle, right? So determine the final speed of the person. If the car is moving at 3 miles per hour, the final speed of the person is going to be roughly about 60, close to 60, not exactly. Final speed of the car is going to go from 30 miles per hour to maybe about 29 to 28. So what's the change in momentum of the person? What's the change in momentum of the car? I got news for you. Action and reaction forces being the same, the change in momentum of the car and the person will have to be the same because as a result, net momentum of the system, total momentum of the system is going to remain constant, whatever that means. Okay, so we had discussion about A and B before. Let's check to see how the numbers work out. Number one, this is one of those problems in real life. The way you solve a problem is called a solution. The solution is usually known as a derivation. Okay, so these problems are not that easy to solve in real life cases. Okay, because you will get an inelastic collision. Collisions are inelastic in real life. Somebody gets hit, obviously momentum is going to get transferred. Aside from that, the kinetic energy is going to be lost. All right, so there's person is going to break bones. There's going to be tremendous amount of heat. There's going to be tremendous amount of sound. Sometimes the person breaks apart. So the real life collisions are inelastic collisions. Okay, so for us to be able to solve problems like this, what we do is we come up with an estimate. Okay, so we have to do an estimate. So we will assume that the collision is elastic. So you will have to look at momentum before impact. So this is the car, this is the person. The car is coming at this person at 3 miles per hour. And then we'll check to see what happens after impact. This vehicle is going to lose some of its speed, and the person is going to fly off. In reality, this person's speed is going to be double that speed, but it doesn't matter. I'm setting up for derivation. That's what it calls. All right, so the question is, what's the speed of the car and what's the speed of the person after impact? Okay, so speed of the person is going to be almost double the speed of the car. The speed of the car is going to be slightly less than the initial speed of the car. So that's what we should get if it's done correctly. Okay. Normally, something like this, if it's an in-person lecture, if I had to do it on a projector or whatever, something like this would take probably an entire lecture time. Okay. Details aren't that important for you guys because it's because I'm not going to ask you about the derivation, but I'm interested in the conceptual understanding of what goes on. Okay. So initial momentum is, so you're looking at the total momentum of the system. So the system composed of two masses. Only this one is moving, the second one is not moving. So the initial momentum is going to be composed of the first mass moving at the speed. The second mass is not moving, so it's not going to have any momentum. The final momentum is going to be composed of this mass moving, so this mass is going to have momentum, so it's this one. So add up the momentum of each and every single mass. Cute. All right, so for momentum before and after, collision is going to be the same. So momentum is conserved. So we end up getting an equation like that. Assume that this is an elastic collision. We were looking for the speed of the first and the second mass after impact. Assuming that it's an elastic collision, which means that kinetic energy is also going to be conserved. So kinetic energy is related to speed, obviously. So the kinetic energy of total kinetic energy of the system after and before will be the same. So this is the total kinetic energy of the system after. This is the total kinetic energy of the system before. All right, and we got two unknowns, which means that you need to have two equations. This is your equation number one. This is your equation number two. Oh my God, this is so awesome. Okay, so you got two unknowns, two equations, and then how do we solve? And that's what we will do. So this gets substituted in right there. Okay, I'm just gonna rewrite the equation so that B2 is gonna be on the left-hand side. All right, so formula is this one. Okay, again, this is the mass of the A. All right, so this is the mass of the first object. This is the car. This is the total mass. This is the initial speed of the car. So the person is gonna get hit by a car. Car is going at 30 miles per hour. All right, so the bigger mass, the smaller mass. The car is moving at 30. The person is not moving. And after impact, what's gonna happen is the car is gonna move almost at the same speed, slow down a little bit. And the person's speed is gonna be nearly twice the speed of the vehicle. All right, so that's what we expect to see. And let's check to see if that's what we will get to see. All right, so mass of the car, the person's mass, the person is 150 pounds give and take. The car is moving at 30 miles per hour. Mass of the car, this is about 5,000 pounds. All right, so what's the speed of the car after impact and what's the speed of the person after impact? Okay, so we had a little bit of, we got two predictions. The car is gonna move nearly the same speed, maybe about 28 to 29 miles per hour. The person is gonna move nearly double the speed of the car. Right, so that's what we expect if the collision is elastic. All right, so we do the conversions. All right, boom, boom, boom. All right, so here's the first formula. This is going to give us the speed of the car. Here's the initial speed of the car. This is the final speed of the car. All right, and we got the numbers, so put the numbers in. And we end up getting about 13 meters per second. This is going to be about 27 to 28 miles per hour. I think it's about 28 miles per hour. So the car's speed goes down by about 2 miles per hour. So that's, in real life, it would be about 26 to 27. So we end up getting 28. That's not bad. Okay, now let's take a look at the speed of the person. We choose the speed of the person. All right, so here's the mass of the vehicle, the total mass, and here's the initial speed of the vehicle. So when you plug the numbers in, it's getting about 26 meters per second. So this is going to be very nearly double the speed of the vehicle. It's going to be almost 60 miles per hour, but not quite. It's 58 miles per hour. Okay, almost double the speed of the car. All right, so it's going to be 58 miles per hour. It's an elastic collision. If it is an elastic collision, this is what you end up getting. So it's almost agrees with what I just said. Okay. All right, so now we made the assumption that this was an elastic collision. Real life is inelastic collision. So what's going to happen is just bones will break this and that. So it's not going to be 58 miles per hour. It's probably going to be close to 55 miles per hour. The vehicle speed is not going to be 28. It's probably going to be 26 to 27 miles per hour. Okay, so now you can make some adjustments. All right, so we figured out the speed. So how much the momentum change, how much the momentum changes for the person, and how much does the momentum change for the car. Guys, isn't okay conceptually. And change of momentum for a system is going to be 0. All right, so net momentum before and after impact is going to be the same. So the change of momentum of the car is going to be the same as the change of momentum of the person. That's what it means. All right, so which means that the motion is going to get transferred to the person. All right, so the motion lost, the momentum lost by the vehicle is going to become the momentum of the person. So momentum gets transferred. That's what it means. So the change of momentum of the person is related to how much the velocity of the person changes within that duration. All right, so initial speed of the person was 0, so we know what the final speed of the person is, so you plug the numbers in. So this is the amount of momentum that the person, change of momentum that the person undergoes. And when you do it numerically, if you're looking at the change of momentum of the car, and when you plug the numbers in, we're going to end up getting the same change of momentum for that. All right, so the momentum that the person gains is going to be the momentum that the car loses in this case. And then the total change of momentum of the system is going to be 0 as a result. All right, so the next thing is, evidently I'm interested in part C. Okay, so what is the magnitude of the impact force? The impact lasts only 1/100th of a second. All right, so we want to express the force in terms of pounds. What's the magnitude of the impact force, if that's the case? All right, so what do we know? The impulse theorem. Impulse is going to change momentum. All right, so we know the duration of the impact. The impact is going to last for 1/100th of a second. That's what we end up getting. All right, so we're interested in the magnitude of the impact force on the person in this case. You end up getting a number like that. Change of momentum of the car is going to be the same in opposite direction, so that's going to give you the reaction force. Notice that action and reaction force are the same, just as expected, and they're about 40,000 pounds. All right, that's it. Okay, that's how I was generating those numbers, the earlier portion of this course. So that's how it is done. Okay, so the thing I want you to know that this was a lot of math for you guys, for those of you guys taking college physics, and you guys are taking college physics. Okay, math is not that important, but I want you guys to be able to interpret the meaning of what we just saw. Okay, so that's what I want to focus on right now.
Next, Detective Walstead reveals
Which means that I want you to be able to interpret formulas, those two formulas that became
the secret behind this game, where you have to get the ball to stay in the tub. There's one game that I see very frequently, almost at every carnival. It's that bushel basket game. And that just annoys me because I'll stand back and watch, and I'll watch people walk up and get cheated because you can't win the game the way it's set up.
You're not going to be able to win this game the way it is set up.
The player stands back.
Why?
Such a
Because this game is unwinnable.
distance.
Okay, and I hate what I just said. Obviously, it's kind of funny at first glance, but seriously, you guys, when I ask you these kind of questions, some of you guys answer it just like that. It's kind of weird. But when I say,
And the angle.
why is it that you cannot win this game? And some of you guys say, because it's unwinnable. That's not what the question is, guys. That's not the answer to that question. The question is, why is it that you cannot win this game? That's what the question is. You can't just answer it because it's unwinnable. All right. What makes it unwinnable is what the question is.
The basket you cannot win.
So the question is, why not?
And the ball won't stay in there.
And so the reason why it's unwinnable is related to
You want to give them the impression that there is a chance
something that these guys understand really well. And obviously, most of you guys lack that understanding.
to win. And it's a good chance. And
They cover his face.
in reality, there's no chance.
There's no chance. You cannot win that match. The only reason why they're going to make it look like you got a little bit of a chance is because they will leave a ball in there.
Sometimes the carny will reel you in with a free throw. But you can bet that's usually rigged too.
It is rigged. So the question is how. And as soon as you have to throw that, he's going to remove the ball.
It's a classic scam right there. What he does is he puts a ball in ahead of time and tells her,
And he made it, from that angle, he made it look like it's going to stick.
go ahead, you throw one in for practice. And what happens is her ball goes in, hits the one
The reason why he went in, because he ended up hitting the side. So the motion got transferred in that direction.
that he put in there, and then
From the angle that you're throwing,
hers will stay in. But when out comes her money, out comes that other ball, I guarantee it. And now here's another game of chance. Fat chance, more like it. Yeah,
all right, so
because the team is to knock down both Coke bottles with one
you're not going to be able to knock both of them down.
roll of the ball. It
It doesn't matter how fast you throw.
can't be done because what the guy
Okay,
does is he'll actually nudge one of the Coke bottles slightly in front of the other, maybe
Okay, and then how does that work?
An eighth of an inch, quarter of an inch. So what happens is when you roll the ball into it like that, the ball hits one of the bottles. There are your clues. See one
Okay, and then you can pay more money and then try to go faster and
in
faster.
front of the other, and there it went. The energy from the ball was absorbed in the first bottle, leaving nothing for the second bottle.
That's cute.
All these little scams add up to big money.
So why is it that it doesn't matter how fast you throw the ball, you're not going to be able to knock down both of them? Okay, so how come you can never win these games?
Get the ball to stay in the tub.
First one, you will never be able to get the ball to stay in the tub or the bucket in the case,
That chance is more like it.
and you will never be able to knock down both Coke bottles at the same time.
The object of the team.
All right, so how do I know that? How do they know that? So let's focus on that for the conceptual portion of the test next week. Okay, there are three cases that we will deal with. Right, three different collisions. Number one, the incoming mass is going to be much bigger than object getting hit. All right, it's like train hitting a person. All right, so the train hitting a person. Person is about, what is it, 170, 150 pounds or something. Train is 10, 20, 30 million pounds. All right, that's the case that you're looking at. Okay. If the train is coming at you at 60 miles per hour, what do you expect? The speed of the train is going to be about it's going to remain at 60. It could be 59.999 miles per hour. The person's speed is going to be double the speed of the train. So it's going to be about 120 miles per hour. Okay, so that's what you would expect to see. So the train is going to be much more faster than the person is. Okay, now the trick to interpreting this is the person's mass is very small compared to the train, so it's negligible. We say it's ignorable, it's negligible. So you just say ignore it. Okay, so if you ignore it, only mass that you have to focus on is the mass of the train. So the mass of the train divided by the mass of the train is just going to cancel out. So the initial speed of the train and the final speed of the train is more or less the same. So the train is coming at 60. After the impact, train is moving almost 60 miles per hour, almost, slightly less than that. But so that's the case number one. So what happens to the person? I said the person is going to move double the speed of the train. Once again, the person's mass is significantly small, so the mass itself is insignificant. So just ignore that because we want an estimate. Notice that the mass of the train is the dominant term, so the masses will once again cancel. Notice that the person is going to be moving roughly about double the speed of the train. Okay, so roughly about double the speed of the train. So the train is going at 60. Now the person is moving at 120 miles per hour. So that's the case that we discussed. What if the masses are the same, like the billiard balls? What if the masses are the same? Okay, so I'm trying to make a decision. Okay, what if the masses are the same? If masses are the same, mass A is going to be the same as mass B. Okay, guys, if masses are the same, what happens here? Okay, m minus m is going to be 0. All right, so which means that this is the first billiard ball approaching at a given speed. So what happens to the speed of this billiard ball hitting this mass? It'll come to a stop because masses are the same. So what happens to the second billiard ball? Now let's go on to this one. All right, so you got the masses are the same, so 2 times this mass plus m is going to be again 2 times the mass. All right, so they will cancel, so you end up being 1 there. So which means that the second billiard ball is going to move at the speed of the first one. All right, so the first billiard ball is going to come to a stop. The second one is going to start to move at the speed of the incoming one. Okay, so you know what that means, right? What that means is the baseball and the Coke bottle, they have identical masses. So it doesn't matter how fast you roll the baseball, because they got identical masses, that velocity is going to get transferred to the Coke bottle, and then this one is going to come to a stop, and the other one is going to keep moving. All right, and then the bushel basket thing goes like this. Okay, so here's the small mass. This is the mass of a baseball. Here's the big mass. The big mass is going to be the wall that you're looking at. Okay, so the baseball is going to be, the mass of the baseball is insignificant compared to the mass of the ball. Okay, now how do we do the interpretation? This time, mass of the baseball is going to be ignorable, so that term is going to drop out. Okay, so if you ignore the mass of the baseball, so what happens? The mass of the ball is going to cancel, it's going to be 1. So which means that the coming ball is going to bounce and it's going to go in the opposite direction at the same speed. So the final speed of the ball is identical to the initial speed of the ball, except there's a negative sign, so which means that the ball is going to move in the opposite direction. All right, here the mass of the ball is insignificant, so compared to the wall, so you can assume that to be 0. So that term is going to become 0. So the masses will become 0. So which means that the speed of the wall is going to be 0. So wall is not going to move. That's what it means. So what happens? The wall doesn't move. The ball bounces back. It bounces back out of the bushel basket at the same speed. Okay, that's it. So everything has been nicely explained. Okay. Okay.